Hello, my name is Jeff Messier. I'm a professor in electrical and software engineering in the Schulich School of Engineering. And in this lecture, we're going to continue finalizing the design of our microarchitecture and add the functionality necessary to do something called jumping and branching. And to just kind of summarize where we're at, this is kind of the second of a two-part lecture. In the first part of the lecture, we modified our microarchitecture so that it was able to execute AVR machine language commands related to performing calculations. So we now have a microarchitecture that can do simple calculations like adding, subtracting, anding, and oring. We also modified the microarchitecture further so that it could load values from data memory into the registers used for calculation. And when we have a result in a register that we want to save, we can write that result back out to data memory. And again, this is for manipulating variable values in data memory, but also in most microcontrollers, the configuration registers that are used to control peripherals like digital I/O pins, A to D converters, D to A converters, and stuff like that, they are basically mapped in data memory as well at special or mapped using special addresses. So we can read and write from those configuration registers using the same load and store commands that we presented in the previous lecture. And so it seems like we've got quite a good little computer here, but we're missing one very important thing. And the thing that we're missing is the ability to make decisions. And that's what jumping and branching is all about. So let's start out by talking about loops. And so this, what I'm showing here is a simple C program where we initialize three variables, A, B, and C. And then while our variable A is less than B, we add the value of C to A. And once A is greater than or equal to B, then we exit this loop and we copy a value into C. So this is a very sort of generic, standard looking program. However, it does something very important that we can't currently accommodate with our microarchitecture design. So when we think about the instruction memory part of our microarchitecture, and I'll just fast forward here to the next slide, this is our instruction memory. So this picture shows our microarchitecture design as of the end of the previous lecture, right? So this microarchitecture can do load commands, store commands, load immediate commands, calculation commands. But the area I've highlighted here in red, this is our instruction memory. And basically, our instruction memory stores a series of 16-bit instructions, and the program counter is incremented by 1 so that we read those instructions sequentially out of instruction memory, so just one after the other. However, sequential execution of instructions doesn't work when we are trying to execute a loop. So when we're doing a loop, basically in order for this to work, we have a certain machine language instruction that adds the value of the C variable to A, and you can imagine this as an add AVR assembly language instruction where we take the value of some register RR, add it to RD, and store the result back in RD. So that's exactly what this line does in C. But we want to execute this line over and over and over again until a condition is true. We want to test the value in A, compare it to B, and keep executing this line of code over and over again until that condition is satisfied, then we proceed. And so basically what we need to do is have the ability to, first of all, test a condition or compare values stored in two variables or two registers, and then move to a particular area in instruction memory based on that condition. And that's what jumping and branching is all about. And we're going to present this in the context of doing loops and if statements. But as we're going to see later on in the course, this concept of jumping around to different locations in instruction memory is really important for function calls as well. So the starting point for our discussion will be the microarchitecture that we left off with at the end of the previous lecture. So this is the microarchitecture, our microarchitecture as it currently stands. And we are going to modify this design to give us the ability to compare values and to potentially jump around to different locations in instruction memory based on the result of that comparison. And just like in the previous lecture, as we add functionality to this microarchitecture, we're going to maintain the ability to execute our previous commands. So we're going to modify our design to add this new functionality, but our new design is still going to be able to support the calculation instructions, the load instructions, and the store instructions. So just to get started, let's go over a few definitions. Let's first of all define clearly what we mean by jumping and branching. So jumping, as the name kind of suggests, is basically just going to a particular location in instruction memory or jumping to a particular address in instruction memory. So as a bit of terminology, when we use a jump command, we usually say that we're jumping to a target or a target location. And the target location is basically the address of the instruction that we are jumping to. And there is actually an assembly language command called jump. And the syntax for the assembly language command is JMP. And then we provide an address. And this address is the address in instruction memory that we want to jump to, or the address of our target instruction. The address is a 22-bit number, and so we can address up to 4 megabytes of memory, which is basically anywhere in the device that that we're using in this class. And so the program counter will perhaps start with an address of 0. It'll then go to an address of 1, then go to an address of 2. But then if we call a jump command, the program counter is updated not to jump to address 3, but perhaps to jump to address, some address other than 3. So basically, jump is implemented by changing our microarchitecture design so that we can modify the contents of the program counter so that we're not just executing instructions in sequence. Branching is basically just a conditional jump command. So branching is when we jump to an instruction memory location or target if a logical test or a condition is true. So we test something. If that test is true or not true, then we jump to a particular location. Otherwise, we continue to execute sequential instructions as normal. And branching is implemented in different ways on different microarchitectures. On the AVR microarchitecture, branching is implemented by calling 2 different assembly language commands. The first is a compare command that compares 2 registers. The format for the assembly language is CP for compare, and then the 2 registers that we want to compare. There should be a comma between those 2. Basically, the way this is implemented is the microarchitecture subtracts these 2 numbers, takes the difference, and then sets the CPU flags, but does not change register RD. So normally when we call the subtract command, RD, RR, this implements RD is equal to RD minus RR. So we take the difference between RD and RR, and then we update the result in RD. Compare does basically exactly the same thing, except it doesn't change the value in RD. However, it does set the CPU flags. That's important because, in particular, if we're testing for equality, we want to take a look at the 0 or the Z flag, right? So if we're testing for equality and we take the difference, RD minus RR, Z will be equal to 1 if the two values are equal. Otherwise, the Z flag will be equal to 0. Another flag that we might want to use in our logical test is the negative flag. So if we're testing whether or not RD is less than RR, when we take the difference, the negative flag will be 1 if RD is less than RR. Otherwise, the negative flag will be 0. So we do this subtraction, we set the CPU flags, and then we call a branch instruction that does a jump based on the settings of the CPU flags. And if you look in the AVR instruction set manual, there's a whole bunch of branch commands. And they have things like branch if equal. So branch or jump to a target location if the two registers that we compared are equal. There's also a branch if not equal. There's a branch if less than command. I think there's a branch if greater than command. The less than or greater than commands would look at the negative flag. The branch if equal or not equal commands would look at the 0 flag. And basically, while there are a variety of different branch commands, they all kind of look the same. So if the condition is satisfied, then rather than adding just 1 to the program counter to execute the next command in sequence, we add an offset k. And k can be a positive or negative number. It's a 2's complement number. And that means we can jump down in the instruction memory address space, or we can jump up in the instruction memory address space. K is a 6-bit 2's complement number, so we can jump so we can have a jump offset of between plus 64 or minus 63 relative to the current location in the program counter. So unlike the jump command we talked about in the previous slide, we can't branch anywhere in instruction memory. We can only stay in kind of the same location. But usually that's okay for things like implementing simple loops, right? So if we're doing a while loop or an if statement, all of our commands are going to be fairly closely located around the same region of instruction set memory. So the format for branch if equal is, the assembly language command is breq, and then we just give the offset that we want to branch, k, and again, that can be a positive or negative number. The branch less than command, its assembly language format is BRLT, and again, we give the offset that we want to jump positive or negative. And like I said, if you're curious, you can look in the AVR instruction set manual and you can see all of the different branch commands that are available. It's super important that the branch command is called immediately after the compare command, right? So you'll notice that in these branch commands, we aren't listing the registers that we're testing, right? Because that's what the compare command was for. So our assembly language will typically look something like, let's compare register 4 with register 10 and branch if they are equal to an offset of -4, right? So these commands occur one after the other. So in order for our microarchitecture to be able to support branching, we have to be able to support both the compare command and the actual branch command. This diagram of our microarchitecture shows the modified version of our design that supports the compare command. And it's basically identical. The compare command has exactly the same machine language format as our calculation commands, add, subtract, and an or. And this makes sense because compare command is basically subtract without changing the register without changing any register values. The only thing I've added is that I have taken the ALU flags and I've fed them up as an input to the control path. Because the compare command is called first, the ALU flags are fed up into the control path, and then the branch command is called second, and then based on the ALU flag setting from the previous compare command, we decide whether or not we're going to branch. But otherwise, this is the only modification. Now, if we look at what our control line settings might be to support the compare command, the memop line would be 0. The load immediate line would be 0. ALU control would be set for subtraction. We don't want our data memory to be changed, so we would set that to 0. And A1 would be the address of our first register. A2 would be the address of the second register that we're comparing. A3 is don't care, because we're not changing any register values. And critically, register write enable has to be 0. Right? So nothing changes in the data path. The only thing that happens is we perform a subtraction, we set the ALU flags, and those ALU flags are used for the next command when we actually call a branch command. And this is the modification of our microarchitecture to support branching. So I didn't pre-draw it on the slide, but this is the machine language format of the branch equal command. So bits 15 through 10 and 2 through 0 are reserved for opcode or used for opcode to identify the command. And bits 9 through 3 store our 6-bit offset. And so I just updated the bits that are the opcode bits that are passed into the up into the control path. Now, the only modification that we have made to our microarchitecture is, as you would expect, some changes to the instruction memory part of our design. Because branching and jumping basically require us to change the value of the program counter to something other than just the next instruction in the sequence. And so we take bits 9 through 3 from our, we take bits 9 through 3 from our instruction and we add them to the current program counter value, and we feed that back to the input to the program counter. We then add a branch control signal and a multiplexer. So if branch is equal to 1, we update the program counter with the program counter plus the branch offset. And if branch is equal to 0, then we just use the next instruction in sequence, just like we always did. And so branch, there's two things that have to be true in order for the branch control line to be equal to 1. First of all, we need to be executing a branch instruction, right? So branch is going to be 0 if we're doing something like an add or a load. But branch also has to be, but branch will also requires the particular condition that it's looking for to be true. So for example, if we are executing branch equal, it is going to look at the 0 flag that came out of the ALU for the previous compare command. If the 0 flag is equal to 1, then the branch control line will be set to 1 because our condition is true and we want to jump to our target location. However, if the 0 flag is equal to 0 from the previous compare command, then the branch control line is going to be equal to 0 as well, even though we are currently executing a branch command. And so the logic, the decision as to whether or not we take the branch or we don't, rests in the control path. So the control path will look at the ALU flags from the previous compare. It will also look at the particular condition that the branch command is testing, whether it's equality, greater than, less than, and then based on that information, it will figure out whether or not to set branch equal to 1 or 0. Okay, so we're finished. This is as far as we're going to go with our microarchitecture design. And you might say, well, wait a minute, like there's a whole bunch that we have left to do. And you're right. So if you look in the AVR instruction set manual, there's a whole bunch of instructions in there that we haven't talked about. There's a bunch of different calculation instructions. There's a whole bunch of different branch instructions, and there's a bunch of other ones that we haven't really touched on. Some notable omissions is we haven't talked about how to implement multiplication or division. We talked about the concept of the jump command, but we didn't actually implement it in our microarchitecture. And also, again, I want to reiterate that the logic design that we've presented for our microarchitecture is super, super simple. So my choices as to where to put multiplexers and, my choice to use a ripple adder and the width of my ALU control bus and all that kind of stuff. This is basically stuff that I've just put together for the purposes of our discussion. It does not reflect how I'm sure the AVR design is actually laid out. So it's a proprietary design, so we don't have access to that information. But the point was to present a microarchitecture that is actually able to execute real AVR machine language instructions. So the machine language that we talked about is 100% AVR fully compatible, and the digital design that that I've shown to you can execute those commands. So in that sense, we've created a fully fledged computer. We have not, however, yet talked about how to improve our design to enhance its performance. So as we're going to see later on in the class, this design basically executes one instruction per clock cycle. So if we go back to our picture here, I'll clean it up a little bit. Fundamentally, our program counter updates on every rising edge of our clock. And so we feed a new instruction into our data path once per clock cycle. And so if we want to figure out how fast our computer runs or how quickly we can do calculations, it's basically one instruction per clock cycle. There are other ways to improve your performance so that you can execute instructions that are faster, or ways you can change your design to increase the speed that you can do calculations at. And we're going to talk about some of those techniques later on. So pipelining is an example of that. So with all of those apologies for the design that I've presented, I still do want to emphasize that this is still a fully functional computer. So even with this very simple design, we can read and write variable values from data memory or I/O registers. We can perform basic logic and math operations on those values, and we can implement conditional statements. We can make decisions on the values that we're working with inside our computer. So this really covers all the bases. And I hope that, I'm excited to get to this point in the class, and I hope that you find this very empowering, right? Because, like I said at the very start of this course, a lot of people say, oh, yeah, I know how a computer works. The CPU is the brain and the memory is how it remembers things and stuff like that. But they really don't know really how a computer works. And if you understand this picture, you understand really how a computer works. So let me, just to reiterate, we have basically built a digital design that can execute real machine language code for the AVR microcontroller. And we've done it using basic logic gates that you would have learned about in your basic digital design class. And so using ands and ors and flip-flops, we have successfully built a computer. And I think that's pretty cool. I think that's pretty kind of a very empowering sort of place to be. And, real microarchitectures are going to be more complicated. They're going to be a bit more sophisticated, but fundamentally, they're not going to be that different than what we've talked about. And now, basically, what we're going to be doing with the rest of the course is just kind of building on this knowledge. We have talked a lot about machine language commands, assembly language commands as we've built this design. We're now going to move into a more sort of full discussion of programming with assembly language, and we're going to get into programming within the actual development environment for an AVR chip, and we're going to see how registers change and memory locations change. We're going to talk about function calls, and then we're going to finish off the class with talking about how we can enhance this design in order to improve performance.